Algebra 2. Notes over section 1.2, transformations of linear and absolute value functions. If you can, get a graphing calculator. I'd like for you to do a little activity at the beginning right now, just so you can see how graphs are transformed. So if you look on your note sheet, the question is, how do the graphs of, and it gives you 3 different graphs, compare to the graphs of the parent function of f? So this notation just means, in general, you have 3 functions. And the first thing is you're having an extra value added to the end of the function. What does that do to the graph of a function? It can be any function, like a linear function, absolute value, a quadratic. The second equation shows a value that has been subtracted to the input of the function. And then the third equation shows that at the beginning of the function it has been made negative. So in general, what does it do when you add a value at the end, when you add or subtract a value to the input, if you make the output negative? So you're going to compare the graph of each function with the graph of its parent function. Use a graphing calculator to verify that your answers are correct. First of all, let's just remember what the parent function are for these. So a, we've got the square root function. So the parent function, I'll just write it in red, would be y equals the square root of x. And that's going to be the same for b, for c. Now let's talk about d. This is a quadratic function. And so the parent function of that will be y equals x squared. And that'll be the same for d, e, and f. On your graphing calculator, you'll see a button in the upper left-hand corner that says y equals. So you want to press your y equals button, and then that will put you into a screen where you see lots of different options. So you'll see y1 equals, y2 equals. These are spots where you can enter an equation and have your calculator graph. So in the first spot, y sub 1, just enter the square root of x. So you'll press your second and your x squared key, and then there's a key in the upper left that has a capital X, T, theta. I'll draw it over here. If you press that key, you will get a variable. Then in the second line, so just arrow down to y sub 2, enter the equation on A. So y equals is already there. You just need to put in square root of x, arrow out of that, use your subtraction key, minus 4. Now, to make sure that you've got a good window, at the very top row of keys, you're going to press your zoom button. And then you're going to press number 6, and that will give you a standard window. Now you should see 2 graphs. The first one will start at the origin and kind of curve off to the right. The second one will be in a different location. So what happens when you subtract 4 out at the end of that square root function? Now do the same for the rest of the problems, B, C, D, E, and F. Make sure when you get to problems D, E, and F that you first put in y equals x squared as your comparison, your parent function, and then in the second line put in the function that you see. And then for each one, write the transformations that you see are happening. Are they moving up, down, etc.? Okay, so check your notes. You should have noticed that on A, when you subtract 4 at the end of the function, the graph will move down 4. On B, when 4 appears to be added inside the input to the x value, it will move left. On C, when you have a negative on the outside of the function, That is an x-axis reflection. On D, you're adding a value to the end of the function, so it's going to move it up or down, in this case up 1. On E, it's going to move the function to the right, 1, off of its original parent position, and then F, you'll have another x-axis reflection. A function can be transformed by adjusting values in the function. The letters that or variables that we use to stand in for those constants, those numbers, are A, H, and K. So if you look at this function, this is the parent function of the quadratic, so f of x equals x squared. You can adjust values, and so you can have A adjust a value. So we know now if that value is negative, then we'll have a reflection. You can add or subtract a value right in by the input, and that's going to move the function left or right. You can also add or subtract a value at the end, and that's going to adjust the graph of the function up or down. Sometimes A values aren't multiplied at the front of the function, but rather just inside by the input, and that is a different kind of transformation, which we'll talk about later in this video. So let's go through example 1. We've got the function f of x equals 2x plus 1. That's a linear function, and the first thing we want to do is we want to write a function, a new one, g of x, whose graph is a translation 3 units down of that graph. So if we remember where these different values can be, I'm just going to write it in equation form. Y equals A times x minus h plus k. So our k values are the one that move it up or down. So we need to, since we're moving down, subtract 3 at the end of this function. And now we'll just clean this up and write this as 2x minus 2. On B, we want to write the function whose graph is a translation 2 units to the left. So let's start with our original, f of x equals 2x plus 1, and then g of x equals, now if we're going left or right, we need to go right in by the input, the x value. So I'm going to open in parentheses, and I'm going to put x plus 2 and insert that just there. And now I'm just going to do the math, so I'll distribute my 2, and then I'll just clean this up. 2x plus 5. Example 2, we've got an absolute value function as our starting function. We want to write a new function whose graph is a reflection in the x-axis. So we start with our original, f of x equals the absolute value of x plus 3 plus 1. Now if we want a reflection in the x-axis, that means all of the output needs to be made negative. So in this case, that is all of this. So I'm going to put negative 1 and then multiply it times everything here. Now when I distribute to an absolute value, it doesn't go inside the absolute value. It simply stays out front. And then I distribute that negative to the negative 1. So this new function will be the one that will be an x-axis reflection. What's nice is if you have your graphing calculator, you can always enter on your graphing calculator the original function and the new function and see if the new function is transformed the way you want it to. Alright, B, we're going to write a function h whose graph is a reflection in the y-axis. So in this case, only the input will be made negative. So we'll take our original function, f of x equals the absolute value of x plus 3 plus 1. And now we're just going to make the input negative. So we'll just make the input negative. So we put a negative right by the x. And then everything else remains. And then we can leave that function in that form. Now on your note sheet, look at the very last page. When you do, you'll see the three core concepts. Focus in on the one that has the reflections in the x-axis and the y-axis. So with these, notice that with the reflections in the x-axis, that the graph of the equation y equals negative f of x. So when the entire output, what y equals, or f of x equals, is negative, then you have a reflection in the x-axis. Here's a good statement of what to do for a reflection in the x-axis. You multiply all the output by -1, and that changes their signs. Now a reflection in the y-axis, so that means the graph is only reflected across the y-axis. It's just the inputs that are made negative. So here you're going to multiply the inputs by -1, just like what we did on A and B. So A, we multiplied the entire equation, what f of x equals, by a negative, and so we got negative absolute value of x plus 3 minus 1. So that will cause a reflection in the x-axis. All of the outputs that were positive are now negative. And then for B, we only multiplied the input by the negative, and that causes the y-axis reflection. Now also look, I'm going to back up to example 1, and let's just go over on that page the core concepts for horizontal and vertical translations. So this is when the graph moves right or left or up or down. So for horizontal, here we go. Horizontal, we've got right or left, and then vertical, up or down. So notice that on those, look at that last statement again. So subtracting h from the inputs before evaluating shifts it left. So you can write, if you look at your equation and you see minus and then the h value position, it's going to shift it right, and then if you see one added, it's going to shift it left. Shifting up or down, if you add k, it's going to shift it up, and if you subtract k, it's going to shift it down. And just remember where those values are. So if we're talking about, let's say, a quadratic function, the a value will be in front, the h value is right in next to the input, and the k value is at the end. A, h, and k are constants. Now let's look at example 3. So on the back page, we're dealing with the core concept of horizontal stretches and shrinks and vertical stretches and shrinks. So example 3 says take that function, the absolute function, absolute value of x minus 3 minus 5, and first of all write a function g whose graph is a horizontal shrink by a factor of a third. With horizontal shrinks and stretches, it's the input that is affected. So our multiplier will go right in by x, and then it is the reciprocal that we use. So if we start out with f of x equals the absolute value of x minus 3 minus 5, then for a, we'll have our new function, g of x, and then I'm going to drop down just so I have space right here where I'm writing. I need to flip that factor, so 1/3, the reciprocal of that is 3, and it just gets multiplied right in by the input. Everything else remains the same, and that will give me a horizontal shrink. So horizontal stretches and shrinks, you remember you have to use the reciprocal and then it's right inside. You multiply the inputs by the reciprocal. Now B is asking for a vertical stretch. So verticals are straightforward, meaning if it gives you a factor number, you use that number. And you're going to multiply the outputs. So that means what the entire function equals. So our new function in this case will be, and I'll take 3, and then I'm going to multiply this entire function. So it will equal 3 times x minus 3 minus it's not a factor of 3, sorry, I had 3 on the brain. It's a factor of 2. So that would be 2 times the absolute value of x minus 3 minus 10. So again, just going over that core concept, for a horizontal stretch or shrink, those are difficult to detect too on a graph. So it's better just to work in with the equation. You're going to multiply the input, so right in the equation where x is, and then by the reciprocal factor. With the vertical stretch or shrink, you're going to multiply the outputs, and then this just by the straightforward factor. Now let's look at numbers 5 and 6. We're going to write a function g whose graph represents just the indicated transformation. So of this linear function, we want a horizontal stretch by a factor of 2. So remember, that means that our a value is going to go right in by our input, and we're going to use the reciprocal. If it's horizontal, we're going to use the reciprocal factor, so we're going to use a half. So our new function g of x will be 4 times a half x plus 2. So g of x will equal 2x plus 2. On number 6, we're going to do a vertical shrink. So the entire output will be affected. And we're going to use the straightforward factor. So that means everything that the function equals will be multiplied by a third. So our new function will be 1/3 absolute value of x minus, and a third times -3 is 1. And now finally, let's look at number 7. So we're going to let the graph of the g function be a translation 6 units down, then followed by a reflection in the x-axis. So we're starting with just the parent absolute value function. So the first thing I'm going to do is just transform that 6 units down. So that means I'm going to subtract a value right out at the end of the function. That's a k value. Now a reflection in the x-axis. So I need all of the outputs to be negative. So I'm going to multiply the entire function by -1. So g of x will equal negative absolute value of x plus 6. And you can, like we've mentioned before, use a graphing calculator to check your answer. You put in your original function, you put in your transformed function, and see if your transformed function is doing what the instructions said, 6 units down followed by a reflection. Let's just do a final cap on what happens to equations of functions and how they're translated. So for horizontal and vertical translations, so that means left or right, the graph is shifted or up or down. It is the h and the k value. So for horizontal, we're going to subtract h, and that will shift the graph right, and then add h, and that will shift the graph left. For vertical translations, it's that value at the end, called our k value, up and down. And you will need to review and memorize where these values are, where they can fall in any function. So the a value is at the beginning, the h value is right in by the input, and the k value is at the end. And now let's just recap our reflections. So reflection in the x-axis, let's try that again, will be when, and one more time, when all of the outputs, or what the entire function equals, is multiplied by -1. In the y-axis, it's only the inputs, so only the x. And then finally, for stretches and shrinks, for horizontal stretches and shrinks, it is just the inputs that are multiplied. But for vertical, it is the entire output, what the entire function equals. And remember, with horizontal, we use the reciprocal factor. So if it says a stretch by a factor of 2, you're going to use a half. But for a vertical stretch or shrink, you just use the given factor.